Okay, hello everyone and welcome. In this video, I'm going to show the central sort of flip that happens in statistical inference, where we go from if we know the population parameters, it's easy to make probability statements about drawing particular samples. But in statistical inference, we want to precisely formulate a statement about the population parameters given our sample. So we're going to suppose that our sample mean is going to be normally distributed with some unknown mean, and so this may or may not be known. For our purposes, we're going to just pretend we know the standard deviation. Okay, so we take a simple random sample of whatever size and we compute x bar. So the question is, what can we infer about the mean of the population that we're drawing from based on our sample? Okay, so by the 68, 95, 99.7 rule, it's safe to say the following. Okay, the probability that x bar is less than mu minus 2 sigma, or that x bar is greater than mu plus 2 sigma, is equal to 0.05. I mean, there's a number of different ways that you can show what I'm trying to show here, but all this is saying is that, you know, if we have our normal distribution, blah blah blah, whatever it might be, got 1, 2 sigma, 1, 2 sigma, there's a 5% chance of being out in the tails of the distribution here. Okay, so from this, let's see. We're just going to let this be statement A, this will be statement B. So we can simplify this to the probability of A or B is equal to 0.05. So we can then say that the probability of not A or B is equal to 1 minus 0.05. By De Morgan's laws, the negation of a union is the same thing as taking the intersection of the negations of the statements. So we can say not A and not B, or the intersection of not A and not B is equal to 1 minus 0.05 is 0.95. So I'm not doing anything too controversial here. So I'm going to go ahead and negate these statements and substitute back in. So this is saying x bar less than this, so the negation of that would be the probability that x bar is greater than or equal to mu minus 2 sigma and x bar less than or equal to instead of greater than mu plus 2 sigma. 0.95. Okay, so we can move things around with this within this inequality here, or with respect to this inequality, and we could say that the probability that x bar plus 2 sigma greater than or equal to mu and x bar minus 2 sigma greater than or equal to mu is equal to 0.95. Okay, so we've got an AND statement, and we've got mu isolated in both sides of the AND statement. So what we can do is we can put mu in the middle, and we want mu to be less than or equal to x bar plus 2 sigma. And from this side, we know that mu has got to be greater than or equal to x bar minus 2 sigma. And we're basically done here. What this implies is that the probability that mu is in this interval is equal to 0.95. So, I mean, it might seem like we've done nothing here, but we've actually done something like very significant, which is that based on the fact that we know that we're drawing, or that our sample mean is going to be normally distributed. We know it's going to be normally distributed about the actual population mean, and we are able to make a probability statement about that in terms of the standard deviation. And then from that, we're able to turn it around and say, look, all of this also suggests something about mu given our sample mean. And what that thing is that there's a 95% chance that mu is going to be within 2 standard deviations of our sample mean. Okay, so hopefully this made some sense, and I can't emphasize enough how important this is for formal statistical inference, because what's happening in statistical inference is we're taking a sample and making an inference about the population parameter. And this sort of train of thought is what allows us to do so. Okay, thanks a lot. Have a good